Machine learning itself, it's really it's a large area, booming today with various application areas. Machine learning gives the ability to extract knowledge and information based on past data and apply this knowledge on future data, simply spoken. And so it really matters how your data looks like and what properties it has. It helps a lot to identify relationships in data, to be able to map certain input to output. That's of course abstract spoken, but we have application cases in various areas. For example, product recommendation. When you go to Amazon and you go shopping online, you find various suggestions. And those suggestions are based on a ranking provided by a machine learning algorithm. Those algorithms are very successful in that domain, and they're called recommendation system algorithms. They have been they are all based on this huge amount of data, on historic data. Going back to my original point about the historic data, we typically need data about the customer to do those recommendations. Furthermore, image recognition and image classification are very widely applied cases for machine learning as well. You might have heard about the autonomous cars. Those are based on computer vision algorithms, which are able to recognize object and do that through various sensors. So machine learning oftentimes has a strong advantage when you have big data, a large amount of data with various signals from many different data sources and sensors, which help you to get good performance on your task at hand. Algorithmic trading is another area, and then of course social media monitoring. In marketing, that's this huge area where companies can get insight into the feedback and then into the thought of the customers and clients through harnessing what's called natural language processing to analyze tweets and other social media comments. That's this application, specifically the classification of tweets into different categories, such as positive and negative comments, is now widely found, and the machine learning algorithms are very successful in that regard. Finally, chatbots. You might have encountered chatbots on websites when you talk to virtual assistants. Those chatbots, they have been also based on what's called natural language processing. There are language models, AI, artificial intelligence, which have been trained on vast amounts of terabytes of text to be able to relate and understand the semantic and syntactic structure of language. Now we do a jump from data to algorithms. And today we want to focus on the decision tree, which belongs to a group of algorithms, which is easier to understand and to explain. They belong to the group of interpretable models, if applied in a certain way. What does it mean? Well, we have a huge landscape of machine learning algorithms. Some are more complex, where the decision making is difficult to understand. Others are more easier to understand. And so you'll find them therefore in different domains, healthcare and medical applications, where it really matters to understand decision making. There, algorithms like decision trees find application, while more powerful algorithms such as deep learning, algorithms with neural networks can be found in domains where individual decisions might not have such an impact if they're wrong and if there are problems. All right, decision tree. As the name says, it's really straightforward. You can draw a tree. You start initially with the stem, and then you can follow maybe through its roots to smaller parts of the roots. And you have what's called nodes, where a stem or a root splits into further roots. It's also something which can actually we will in a moment in that format analyze and talk a little bit about the power of and the application of such a tree, of such a decision tree. So for example, here we have a tree where I would call this perhaps the stem up here, from where you imagine the tree top up here, and then the stem, and then the roots following through in a directed way towards the bottom. And we call those intermediate steps, for example, here split into different outcomes, false or true, for example, as a node. And so these are decision nodes, which can result in 2 or more branches. Yeah, here we have our branch in false and true. And each lead node represents a decision. So now you might say, which decision? So it's all about the decision of the algorithms. The algorithms learn, the decision tree learns to make decisions around variables it chooses in your data. Sounds like magic, but we're applying that the decision, we give the algorithm the chance to improve its decision making, which choice to make at each of those nodes based on historic data, and we optimize it with optimization methods, numerical and such. We also decide on which nodes we want to split based on criteria. Yeah, you might say, okay, here's a node. Which criteria do you want to use for splitting? It depends, of course, on your data. And typically, we split based on variables in our data. So we have, for example, certain variable A, or variable called windy. Yeah, if it's windy, well, then we could split to the right. If it's not windy, it's split to the left. And which option you have are based on the data at hand. It's how you split and which data comes to the left and right. The split threshold, I could say, depends on the Gini impurity and the mean squared error, for example. So on certain measures and metrics to be used. Here you see an example of a tree. Now concretely, for we want to predict golf playing hours, let's say for the week. Yeah, hypothetically. So if you want to go ahead and doing this, you might think, okay, on which kind of data do I have to predict those golf playing hours? And so let's assume we have data about the weather, and this weather data maybe can help us to make a decision about if somebody wants to play golf or not. We can establish a decision tree as follows, where based on the outlook, the weather outlook, we could follow a different outcome. Here, for example, if the weather is sunny, then we would be here. The outlook is sunny, apologies. And then if it's windy, and if it's windy, yes, we would go down here this path, and then finally end up at a certain root here. Yeah, the deepest roots of our tree down here. And they're called leaf nodes. And those leaf nodes, they're telling us how to make a decision. Because if I, for example, look at let's say a certain day of the week, and I follow this decision tree path, sunny, yes, windy, yes, I end up with a certain amount of hours per day, on which, sorry, per week, which I want to play. And this kind of tree is now not something I provide beforehand. Again, it's being built based on the data. So in my data set, which helps me to build this tree, I have the variable outlook, I have the variable windy, and the variable temperature, right? And so those variables I can combine in various ways to make decisions. I know for a fact, though, that all the outlook, for example, has only those 3 categories. Windy has only those 2, and temperature has only those 3. And now we could build various versions of a tree where in each version we have, let's say, all those 3 nodes present, and we would make a decision based on those 3. In fact, there are so many potential combinations to build a tree that it's impossible for an algorithm to test all combinations. That's why decision trees are actually making what's called a greedy decision at each point. So we're building a tree from the top to the roots, and at each point we are evaluating, at each node we are evaluating which kind of variable do we use. Do we want to use windy here to make a decision, or do we want to use temperature, for example, here? Yeah, which could lead to a different tree. Perhaps we're also not using temperature at all. So we leave the algorithm the choice to make in regards to which variables to use and which decision to make. Here we have again the weather type, for example, rainy, humidity high, and windy false. Yeah, you could build a tree, a decision tree based on those 3 weather-related variables, and then have an output from the algorithm, from the tree. If we want to go though, and we want to get a real performant algorithm, we would want to use multiple trees. And you might say, what's the advantage of multiple trees? And the combining multiple trees has the advantage that if each tree makes a certain amount of mistake, that with many of them, it's unlikely that the average or many of them make the same mistake. It's not likely, and they are independently built. And as a total, as a crowd, as a group of trees, if we take all their results and, for example, take the result which has the most decisions, or which is the average value, then we can get a better result. This is what's related to the concept of wisdom of crowds, where we know intuitively if you ask more people and you consult more, then we get a better opinion or a better result. Here we apply our result now, our table on the decision tree. So we essentially build out of those 3 variables a decision tree, and then apply this data point here, this week, let's say, with the results, where we know this week it was rainy, the humidity was high, and it was very windy, or not windy, apologies. Then we could use the decision tree to identify about the outcome, if it's worth, for example, playing golf, yes or no. You see here we have similar variables, but the outcomes have changed. Actually, this is a decision tree where we didn't want to predict, let's say, the golf playing hours, but instead we wanted to predict if it's worth playing golf or not, or if somebody will play golf or not. To make this actually a concrete case, we could go ahead and collect a lot of information, a lot of data about an individual's, golf activity. And that would include, for example, many rows like this, where we have rainy, where we have weather type information, humidity, and windy information. And this kind of information, where we have then each row, it's a kind of the information, let's say, for the person's decision to play a golf or not. And so if you have many of those, our goal is to build a decision tree and to then identify and hope that the decision tree can then help us to make a decision about this individual. Yeah, will this person actually play golf, yes or no? And this decision tree is the outcome of an algorithm which has been trained to make a decision of yes and no. You see here, both the tree's outcomes are just yes and no. That's what's called a classification algorithm, because we have different classes of outcomes. Okay, so yeah, that's a very powerful way to make decisions through this tree. We can also explain this decision of this tree very easily. Now I go back to the fact that this is a very interpretable algorithm. You can understand if we have this data set, you can explain to anybody based on this tree why the decision has been made. For example, here it's rainy, the humidity is high, and then apologies. So we would go to rainy, and then yeah, let's say humidity high. If we would get and we ignore the windy for now, we would get play golf as yes, as high. So that's sorry, here to no. So we would identify it as no. So the person would not play golf. So here we have the output, and that's explainable in an effective way. So now we use our random forest, where we have multiple decision trees built. Our algorithm uses historic data and then builds a decision tree with different variables. For example, here, this decision tree is just based on the weather type. It's a very simple tree. If the weather type is sunny, yes, we want to play golf. If it's rainy, no. And if it's overcast, then we want to play. Here we have a second tree based on humidity and then the weather type. Now, if we build more of those trees, when we then take into account all the outcomes, we can take a majority vote on the outcomes to choose what should be our final decision. For example, here, no, no, and yes, would put no in the majority, and our outcome would be no. Now, this is a very simplified picture. You might have in practice many more variables, and you have to make the decision about how to configure your decision tree or random forest model. So we have typically use cases you work on the weekly basis, real data, where you get a context background and then have to solve those business related problems. As a mentor, my role is to support you in this process through sessions. And I will dive more into this later. So for our case today, we look at the production of renewable energy because of the global warming. That's a very relevant topic for us. And one of the very effective ways to produce energy is through wind. And of course, wind is a resource with little control. It can happen that we don't have enough wind, will produce less energy. And so it might be good to actually get some idea to predict perhaps the energy generation. And so based on different variables. So we put on the head of a data scientist working for an environment NGO. And so our goal is to apply machine learning and to get insights into the energy production. Now, let me clarify in a moment, what does that actually mean? We will see that when we understand the data a little bit better. But at the high level, our high level goal is, can we predict the power production? And so in the first step, you actually, even before we go into the exploratory analysis, the questions emerge. What do you want to predict clearly? What kind of variables are available? And if so, what is the quality of those variables, for example? Those choices are crucial. And I get asked a lot, how much data do I need? How much do I start with that machine learning works? And in a way, there is no clear-cut answer. The performance of machine learning depends on various aspects, on the problem case, on the quality of the data, and what choices you make along the way. And that's why it's important to learn the process of how to go through machine learning projects end to end. And in this course, you cover those aspects. There's a strong business focus, but there's also the basics and applications from classical machine learning to deep neural networks. And then you have the feedback from the mentors, and yeah, insights shared. So after we get an idea, which can take also weeks potentially to get an idea about the data available, and you can get access to the data, then the first step is typically the exploratory data analysis, where we want to get an overview over the data. Now there's a somewhat standard way to do this exploratory analysis with steps typically recommended, including the detection of missing variables, for example, data quality issues, looking at individual variables and such. And once this is done, you can make choices about how you change your raw data, and that the raw data might have flaws such as missing values, and you want to impute those missing values. You might need to encode your variables. Encoding means you change its representation. You change it, for example, from a categorical value, from a text to numerical values or such. And you do your split into training and test sets. So what does that mean? You split your data into different data sets, because we are in machine learning. We oftentimes want to evaluate our algorithms on, it's called test data, which is set past that additional data we have not looked at much to evaluate it empirically. So empirically, we do a lot of evaluation. In reality, it's oftentimes that you find there are missing values, you have issues with the data, and you start back with requesting more data or other types of data. And this pre-processing and exploratory data analysis can take the majority of your time. Variable encoding, for example, can also depend on the next step in our analysis, where after you understood your variables well, their properties, maybe have built some hypotheses around those, you can start building models and decide which ones to use. There are many different, there's a model zoo out there of different types of model, which you can categorize according to model complexity, according to interpretability, according to the type of technical, if it's a probabilistic model or more deterministic or such. There are various aspects, and it's not easy to make choices which one to use. Yeah, so that's why it's good to get a breadth of information about those algorithms before you can actually make a choice. And so what has emerged is also that there are specific algorithms for specific problems at hand. Take computer vision, where we process images, for example, or video. They have certain types of algorithms very successful. And then you have algorithms which process text very effectively. And you would end up with specializing. When you work on a problem, you will specialize yourself in a certain area and apply those and learn about those algorithms and apply those. And then finally evaluate the results. Okay, and the conclusions drawn, there are practical ones, insights through the EDA, for example, which you might find already useful to draw conclusions, relationships, correlations, such as, for example, which can help you to already provide value. And then there are the other conclusions around model performance. Typically, at the beginning, when you define your business objective, you define KPIs or metrics which are tied to model performance. And in the end, you can make a decision about, is my model good enough? to actually use it in production or not. So now we have learned about the process. Let's go straight on this actual data set. So we have over 27,000 windmill configurations. And so each of those configurations is in a one row here, where you see the column information. The columns are different variables, such as the wind speed measure at atmospheric temperature and such. And then the rows are the different measures at different times. Specifically highlighted is this generated power variable, which we call in machine learning oftentimes the label or the target, which is the quantity we want to predict. Yeah, so oftentimes when I start off a project, the question is which variables could help us to predict the target. And you might think about, well, what's already known before? Maybe somebody else has already in your own business has already done some work without machine learning and has identified there are relationships with variables. For example, that the wind speed matters very much for the generated power. And so you would, of course, include those variables in your model. But there might be other variables, which I have experienced multiple times, which we took from external sources, from open data sources, such as weather data, and use those to enhance the existing, enhance the portfolio of data we have and improve the model based on this external data. And here you can imagine that as atmospheric data, for example, those, for example, and the wind speed might actually come from an external source. And as a data scientist, your job is to look into those, to identify those sources, to extract the data, and to see if it can provide additional value. One thing to note is, however, that your choice of variables needs to be, which you want to use in a model to predict the power, needs to be closely aligned with the business objective and also with the setup of the application of your machine learning algorithm. Now imagine this scenario where our goal is to predict the windmill generated power, let's say a week in advance. Okay, so if I want to do this in a week in advance, I need to think about, well, what kind of problem this is. This is somewhat a time series problem, time series application. You have a historic series in a way, and you predict future values. That's not always the case in machine learning, but here it is. And then which variables can I actually use when I make those predictions? Yeah, it might be obvious that the shaft temperature, for example, which I interpret as a part of the wind turbine, might not be available a week in advance. And so building this model on those might be, for the specific case of ahead forecasting, not useful. In fact, that's this kind of usage of variables which are not available at the time, or perhaps only after the time of when we want to have the model results, the predictions, are called data leakage, or information leakage. Yeah, that can happen when you assume a variable is available, before we want to do the target predictions, but it's actually available only afterwards. So, for our case, we decided to include information which, shaft temperature, and as much as possible for now, as an initial starting point to see which variables are strong predictors of our outcome. And we might exclude some of those variables later if we want to include it, if we want to consider that 1 week forecasting. Also, it matters how those variables, which kind of orders of magnitude they are, kind of properties they have. We will look in a moment about in those variables. So typically, we look at, for example, this one, wind speed. We look at the distribution of the wind speed. You might have some subject matter knowledge to apply, and you do this with other variables as well through this exploratory data analysis to understand them well and verify them. Let's go through this. As on the example here, we look at the we plot the results is a histogram. So here we have the power generated, which is our target variable. And one of the first things you really want to look at is the distribution of the target variable. And you want to identify what kind of distribution is it. Is it a bimodal? Are there 2 peaks? Are there 3 peaks? Because the choice of the variable, the distribution can give you insight about what kind of challenges you might face when you predict those results. I imagine we have here, as you see here, it's called skew to the right, and here are a few values only where there was a lot of power generated. Now, if I have only a few values down here and I build a model to predict the power generated, you might think that, well, if historic data matters a lot and the model derives information from the data, it might be very good at predicting where the most data is. But if I go to up here where apparently the wind turbine was rotating like crazy and producing a lot of energy, maybe for that part we don't have actually much data, and a model trained to predict in that area to predict actually the kilowatt hour is actually this might be actually problematic. Another point to consider, if you look at here the motor torque, which is one of those variables in the rich set we have, you look at it and you see pattern appearing. Yeah, well, why are those patterns appearing? This is a usual question. Why is it distributed this way or not? One could guess maybe there are different modes of operation for the motor of our wind turbine. Maybe there are certain conditions which make produce a lot of motor torque around in this peak and this peak, and why are they different? So we need to understand the distributions. I want to also highlight that this data we collected here of those 27,000 windmill configuration that comes from different times, and as such there might be changes to the wind turbine over time. That's called data drift. It's a natural occurrence with all data, and machine learning algorithms are very sensitive to this. What I mean is that if the machine learning algorithm learns certain relationships, let's say motor torque affects strongly the power generated, and then it predicts motor torque, predicts power generated based on a certain motor torque value, and this relationship suddenly changed because our motor starts to break down or having issues, the machine learning model will have problems. So the data drift is part of what's oftentimes faced in real applications and during production. And this is where I believe mentors can share a lot during the course, because they have experience applying those and monitoring those algorithms, which is a different beast from what you would learn just by looking at the theory course. We can look at other information at other variables and the distribution resistance, for example, and the generator temperature. Here we again have a very particular shape and then distribution. When I start a project, typically I'm not an expert in that domain. And if you're lucky and you work in a certain domain area, and you're an domain expert already, and you apply machine learning, then you're better set up. I've worked on different domains such as healthcare or econometrics, and I found it takes a while to get. You need to understand the data and its properties, and I work closely with the domain experts on different projects, because we as data scientists, we need to be comfortable understanding the variables because our model will just objectively derive information from those models without our guidance. It's our job to evaluate the data quality, the distribution, and then also the results from the algorithm. We have now so far, we looked at individual variables, but after we identified that we want to predict the windmill power, the power generated, it's relevant as part of the EDA to look at the relationships between the power generated and other variables at hand. If you have a few variables, great. It's easy to identify relationships. If you have thousands of variables, We have to apply other methods, maybe first dimensional reduction techniques, for example. But after doing this, we want to look at, for example, here the cloud status. So how's the weather? Do we have a lot of clouds? It's a lot of clouds. Are there some clouds? And then do plots like this. Here we have, this is called a box plot, where we see the windmill power generated and its range for different cloud status. Now, something obviously comes to mind here is that, well, if we have very little clouds, it seems like the windmill generated, power generated is very, very low, low amount of power generated. But if I go to higher, or at least low and medium, I see there's more generation of power. This is an insight I can just visually observe and then create a hypothesis, which is if the results, if the weather status is extremely low, we don't expect much power generated. And I could go back to subject matter domain experts to verify this hypothesis. And I can also verify that later when I build my model to ensure the model has come to a similar conclusion or has derived similar relationships. Yeah, I have not talked much about the plot itself. This is the median here. This vertical line is the median of the distribution. And the median is a relatively good measure to summarize data, and it gives us a location. Essentially, half of the data points are on the left side, half of the other data points are on the other side. So that's a measure of what we call central tendency. You see where most data is. So that really tells us that here there's most data at very low energy generated. If we look at the turbine status, we have different categories for the turbine. And looking at the windmill power generated, you actually see there's not much of a difference. So this variable might have a low predictive power. But we have to be careful because here we really look only at a slice of the data. We look at the relationship between one variable and our power generated. There could be nonlinear effects, yeah, which we're not seeing right now, which can be discovered by nonlinear models. And so we have to be careful with these decisions. Also, how to highlight is we have here those categorical variables. We have numerical variables, the numerical value, the power generated, and there are different techniques in which kind of variable types you have. And we discussed this typically in the course about which kind of variable we have, which kind of decision of plots you can make to have so that you have a roadmap of how to process with the exploratory analysis. And yeah, then we have the bivariate analysis, where we look at the correlations between the different variables. So here you have this very colorful matrix where up here you have all our variables, and here you have the same variables again. And all the numbers in those boxes are linear correlation factors. They give you an idea about how strong the correlation is. The range is fixed between -1 and 1, and values, for example, between closer to 1, very close to 1, that means high correlation. Here, for example, this is the generator temperature and the motor torque. There seems to be a very strong relationship. And so we have to make a decision which variable to include and which not based on this. For example, if I have a linear model, I might not include highly correlated variables and exclude some. So this is an analysis. We can see we identify the highly correlated variables. Careful because it's linear correlation. There can be, again, nonlinear effects between variables which you don't see in such a diagram. Yeah, so data preprocessing, you typically have missing values in your data. There can be because of issues with the data, because somebody made a mistake in the processing. There could be also missing values naturally because data was not collected, cannot be collected during certain times of the day, perhaps. And then we have the different categorical variables, and we have to standardize them in some cases. What I want to highlight is the splitting the data. When you build your algorithms, we want to evaluate the algorithms fairly objectively, as much objectively as possible, and also empirically. So you apply your algorithms on other data you have hold out, and which data you hold out and is actually not an easy answer. The standard way oftentimes it's a random split, that some 50% you draw random data, you have half of the data, maybe 30% the data goes into your test set, which you evaluate your model, 70 is for training. But those random splits, they have caveats, and especially when you look at practical applications, oftentimes splits along the time axis are more relevant, and stratification to recover distributions and have a good representation of distributions and of the population, that's more important. And that's what's covered in the course. We chose this model, random forest, because it's a pretty powerful model and algorithms, which has been used in various applications, even in the application of image processing and image classification. And so what we do is we build our algorithm based on those 10 trees, our regression, and we use them in the form of a regression model, because we want to predict the energy produced. The energy produced is a numerical value, so we want to produce and predict and create as an outcome a numerical value. So our tree needs to map from those variables we discussed before, the motor torque and the pressure, atmospheric pressure, and so on. And we hope that the model somehow discovers a relationship between those variables, like the pressure and the energy generated in the turbine. And so once we have done this, we have built an algorithm. We can analyze its performance for different slices of the data, maybe certain types of the day, which is typically done then to understand if there are variations in the performance and potential challenges. And also we can get an idea about the error the algorithms make. That's also important. So we need to have a confidence in the predictions. And there are different machine learning algorithms which can give you an uncertainty, a measure of uncertainty around the algorithm. And one, for example, here that here we have an uncertainty band, so which gives you an idea about how much error there is around your predictions. Finally, as a step in machine learning building, you want to analyze the importance of your features, because it helps you to evaluate the model itself. Does it perform actually as expected? And it also gives you insights for your business case. For example, in our case, where we applied all those variables in our random forest, we can identify feature importance by model, by variable, and see here that the motor torque is actually a strong predictor with a large feature importance, while the shaft temperature and wind direction actually contributed very little. There are more complex methods to analyze importance of features. There's a whole field called explainable AI, which is also booming, to get better insights into the contribution of each variable. Okay, so wrapping up, what have we learned through our project? And we have first learned through the EDA that there are certain variables which are correlated with each other, and specifically that the motor torque is highly correlated with the amount of power. I can see that through diagrams, but we also can see that through the model feature importance in the last slide, which is very high. We can also see which were surprises sometimes to identify surprises. For example, the blade angle actually contributed quite a bit as feature importance to the prediction. And so then one step would be to say, well, if we aim to want to optimize perhaps the energy generation, can we identify which blade angles based on the model and our analysis, which blade angles are actually effective to generate more energy? And those results, they can be then provided to optimize the engine. There's this area of counterfactual analysis in machine learning, where we're asking the question, what if, in a way, what if the blade angle is changing? Does that change dramatically the outcome of our prediction? And so that's another helpful tool, counterfactual analysis, when you analyze your results. Also, if we look at the model and we can say the model predicts the power generated within 0.3 kilowatt hours, then maybe it's sufficient. It should, if it meets the KPIs and the metrics we defined earlier together with our clients, then we are within and we can deploy this model. If not, we might have to go back and identify better variables and improve the quality of those. So that's oftentimes also done. Not every project is successful because we don't know beforehand if the data we have is sufficient, has enough sensors, enough signal in there. So those machine learning projects, they have no guarantee to meet the KPIs and the metrics, and that's has to be always communicated from the start. It's an innovative project. That's why oftentimes organizations execute multiple projects to identify then the ones which are then the successful ones to proceed